We will start our problem with a square. Then, inside this square, from the bottom left corner to the top right corner, we will inscribe a quarter circle. Now, inside this quarter circle, we will first inscribe one full circle, which is going to touch the arc of the quarter circle, and it is also going to touch the right side of the square, as you can see on the sketch. Next, directly below it, we will construct a half circle which will have the same radius or the same diameter as our full circle on the top. And as you can see, those two circles will be perfectly aligned, so this basically means that you can also pull a straight line on the left, and this line will be the tangent to both of those circles. Now, on the remaining left part, we will first construct a small square with the area 1 on the bottom left side of our sketch. The question is, can we somehow calculate the area of this golden shaded rectangle on the top left? To be honest with you, I wanted to do this problem for quite some time, and I was first introduced to this problem when I was in high school. And it will have an awesome solution. So you guys can pause the video right now. If you want to, you can try it out for yourself and then you can come back and check the solution. Alright, so let's solve this problem. So first I'm going to label all the vertices of our square as A, B, C, and D, and then I will label the remaining vertices of our smaller square and our rectangle as E, F, G, and H. Then I will also label two centers of our inscribed half circle and full circle as O and Q, as you can see on the sketch. I will leave this notation so that you guys can have this as a reference if you want to post your own solutions in the comment section. So I will start by labeling the radius of our inscribed full circle as small r. Then I will rotate this radius horizontally, and I will get that this radius will actually be perpendicular to the right side of the square. We know this for a fact by using tangent of a circle theorem, which states that if we pull a radius to the point of tangency, this radius will always be perpendicular to the tangent line. And in our case, BC is actually the tangent line of our circle, so this means that BC must be perpendicular to our radius. Now you can notice that the angle at the point B is also the right angle because ABCD is a square. Then we can pull a vertical line from Q to O. Now we can slide this radius along this line downwards, and we will again get that OB is also equal to small r, but this is also the condition of our problem. Next, since OB is equal to r, this means that OE must also have the value of small r. And now, if we rotate this radius vertically up along the line OQ, and if we do the same for the radius of our circle on the top, we will get a straight line. We actually know that this is a straight line due to the fact that those two circles have the same diameter and they are aligned atop of each other. And if you're still not convinced, you can use one really interesting circular theorem to prove this, which states that if two circles touch each other externally or internally, then their point of contact lies on a straight line joining their centers. And as you can see, this is exactly our case here. Next, we will label the side BC of our square as capital R. And you can notice that this side is also the radius of our quarter circle. Now we will rotate this radius to the point Q, and if we do this, this radius will touch the contact between this quarter circle and our full inscribed circle. We're going to do the same for the radius of this full circle. We're going to rotate it to the same point of contact, and if we do this, we will again form the straight line. Now, in order to prove this, you can use the same circular theorem as before, only this time we will use two circles that touch each other internally. Then, again, their point of contact will lie on a straight line which joins their centers, and as you can see, this is exactly our case. This leads us to conclude that the remaining segment QB will have the value of capital R minus small r, or it's going to be equal to the difference between those two radii. Alright, so now let's focus our attention to this newly formed right-angled triangle QOB, and we can use the Pythagorean theorem. We can say that hypotenuse BQ squared is equal to the leg OB squared plus the leg OQ squared. Now we're just going to substitute the values from our sketch. Then we're going to expand the left side by using the square root binomial, and afterwards we're going to cancel r squared on both sides of the equation. Then, if we group all our terms on the left side, we're going to get this really nice quadratic equation. And we're going to solve this equation in the terms of capital R. In order to do this, we're going to use a quadratic formula. And just as a quick reminder, if you have a quadratic equation in form of ax squared plus bx plus c, which equals to 0, you can use the following quadratic formula. I have used this formula in quite a few problems on my channel, so you can check out some other videos and you will find the implementation of this formula. Now, if we take a look at our quadratic equation, you can probably notice that coefficient a is equal to 1, b is equal to minus 2 small r, and c equals to minus 4 small r squared. Now we are just going to implement those values in our quadratic formula, and we will get the following. Now we're just going to work through this. First, we're going to work through the terms inside the square root, and then we're going to add those terms. After which we can simplify this square root and get 2r root 5. Now you can see that everything is divisible with 2, so we're going to simplify it and get the following. From here we can actually isolate small r as a common factor, and we will get two possible solutions. The first one is that capital R is equal to small r times the quantity of 1 plus root 5, or the second one, which states that r is equal to small r times quantity of 1 minus square root of 5. Of course, you know that square root of 5 is a number which is bigger than 1. So this means that our solution on the right cannot be valid because it will give us a negative value. So this means that the only possible solution is the one on the left. Now, let's take a look at our sketch again, and let's have a look at the small square on the bottom left side, AEFG. This square has the area of 1, which means that it has the side of 1 as well. Now we can slide the bottom side of the square AE vertically up, and we will get that DH will also have the length of 1. Now let's have a look at the diameter EB of our semicircle. This diameter, EB, along the side of the bottom small square AE will form the side of the square. So now if you take a look at the left side of the square, AD, it consists out of line AG, which equals to 1, which means that the remaining side, GD, must have the length of 2r, which is equal to the diameter of our half circle. Furthermore, if you take a look at the side CB, which is also the side of the square which we labeled as capital R, you can see that this side equals to the side AD. This means that capital R must be equal to the sum of the segments 1 and 2r. Now we will just substitute the value of capital R and get the following. Then we will expand the left side of the equation, and then we will group all the terms with small r on the left side of the equation. After simplification, we will get the following. From here, we can again pull small r as a common factor, and we will finally get that small r is equal to 1 over quantity of square root of 5 minus 1. Alright, so now remember we are looking for the area of our golden rectangle GFHD. And the area of this rectangle equals to the product of its base and the height. In our case, this is 2r times 1, which equals to 2r. Now we're just going to substitute the value of r, and we will get that this area is 2 over quantity square root of 5 minus 1. Of course, we're going to rationalize this, and you can see that in the denominator we will get the difference of squares, so it will be equal to 5 minus 1, which equals to 4. Now we can simplify 2 and 4, and we will finally get that our golden area is equal to square root of 5 plus 1 over 2. And now, all of you math lovers out there already know what this is. And if somehow you're not familiar with this number, let me put it in decimals. This actually equals to 1.618, etc., etc. And yes, this is the number which we call phi in mathematics, or you probably heard its other name, which is golden ratio. And you can find this number anywhere in nature, from galaxies to snails, to human bodies, to leaves, and a lot more other examples. And I'm also planning to do the video about the golden ratio sometimes in future. But until then, this is our golden solution, so the area of our rectangle equals to phi. So I hope you guys enjoyed this golden problem, and if you did, do not hesitate to leave a like or subscribe to the channel for more content. Of course, if you found another way to solve this problem, please post it down in the comment section below. And until next time, see you all and take care.